Okay, I have a scenario for you. It's a little dark, so just go with me for a second.
All right, I'm ready.
Imagine a total cataclysm. Everything we know is wiped out. Libraries are burned, servers are melted, every textbook is just gone. Civilization is basically hitting the hard reset button.
Well, that is a terrifying way to start a deep dive.
It is, but here's the kicker. In this scenario, we get to pass on exactly one sentence to the next generation of creatures. Just one. One sentence that contains the most information possible to help them rebuild the world. What do you say?
See, my instinct is something practical, like wash your hands,
Yeah.
or maybe don't eat the red berries.
Right, or be nice to each other.
Okay.
But I'm posing this question because it was actually a hypothetical set up by Richard Feynman. And his answer wasn't about hygiene or morality. It was about physics.
Ah, Feynman, the bongo-playing Nobel Prize winner.
The very same. So today we are diving into his legendary collection of lectures called 6 Easy Pieces.
These were the lectures he delivered to Caltech undergrads back in the 1960s, right?
Exactly. And just to give some context on Feynman, if you're not familiar, he won the Nobel Prize in Physics in 1965. He worked on the Manhattan Project. He investigated the Challenger disaster. And he was a massive pioneer in quantum computing and nanotechnology. So he knows his stuff.
He absolutely does. He was brilliant at making the complex accessible.
And that's our mission today. We're looking specifically at what he called the atomic hypothesis. Because his answer to that cataclysm question, the one sentence he would save, is this. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another.
That is quite a mouthful for one sentence.
It really is. And honestly, when I first read that, I was a little underwhelmed. Like, everything is made of atoms. We learned that in 4th grade. Why is that the golden ticket to rebuilding civilization? Why not relativity or germ theory?
That's the brilliance of it, though. He isn't just stating a fact, he's handing you a key. If you really understand that sentence, that everything is granular, everything is moving, and there's this push and pull force, you can derive almost all of chemistry, biology, and physics from it. It's basically the source code of the universe.
So our goal today is to test that. We're going to look at the everyday world, a glass of water, a burning fire, a smell, and see if we can explain it, just using Feynman's atomic lens.
I love it. But to do that, we have to adopt his mindset first. You have to stop looking at the world as static objects and start seeing it as a dance.
A dance?
A chaotic, billion-partner dance. Let's take that glass of water you just mentioned. Imagine you have one sitting right in front of you. To the naked eye, what is it?
It's wet, it's clear, it sits there. If I don't shake the table, it's perfectly still.
Right, it looks continuous. But Feynman says, let's magnify it. Zoom in a billion times. What happens to that smoothness?
It breaks apart.
Completely. You see billions of tiny particles stuck together in little clumps we call molecules. And here's the crucial part that I think people forget. They are not sitting still. They are jiggling.
Jiggling, is that the actual technical term?
In Feynman's world, yes. It's perpetual motion. Even in a glass of water that looks dead still on your desk, those atoms are crashing into each other, spinning, vibrating. It's a literal mosh pit.
Okay, so if it's a mosh pit, why doesn't the water just fly apart? Why does it stay in the glass?
That's the attraction part of his sentence. When atoms are a little distance apart, they pull on each other. They genuinely like to be close. That stickiness is what makes water a fluid. But, and here is the weird duality, try to squeeze them.
Like if I tried to compress the water in a piston.
Exactly. You'll find it's almost impossible. Water is incredibly hard to compress because the second part of the sentence says repelling upon being squeezed into one another. Atoms are like people. They like being in a crowd, but if you step on their toes, they shove you back. Hard.
So the water is static because it's caught in this deadlock. It wants to be close, but not too close.
Precisely.
Yeah.
It's a dynamic tension. The jiggling is trying to blow them apart. The attraction is holding them together, and the repulsion keeps them from collapsing. All that dramatic action is happening in a quiet cup of tea.
That makes it feel so much more alive. But let's play with the jiggling part. What happens if we change the amount of jiggling? Because that's what we perceive as temperature.
Yes. In this atomic view, heat isn't a fluid or a magical substance. Heat is just the measure of how much the atoms are moving. So picture a block of ice.
Yeah. Cold solid.
In a solid, the atoms are still jiggling, but they are locked in place. Feynman uses this great analogy of a regiment of soldiers. They are standing in rows and columns, but they're shivering, they're fidgeting.
So they have a specific seat, but they just can't sit still in it.
Right. Now you add heat. You light a fire under the ice. You are transferring energy to those soldiers. They start shivering more violently. The jiggling increases. What happens eventually?
You break formation.
Exactly. The shaking gets so violent that the attraction can't hold them in their rows anymore. They break rank. They start tumbling over each other, sliding around. The rigid structure is gone, but they're still close enough to touch.
And that's melting. That's liquid water.
That's a liquid. Now keep cranking the heat. Give them even more energy.
I assume they start moving so fast that even the basic attraction isn't enough to keep them together.
Boom! They fly apart. They literally launch themselves into the room, bouncing off the walls, completely separated from their neighbors. That is steam. That is a gas.
So the only fundamental difference between an ice cube and a steam burn is how fast the little guys are dancing.
That's it. Same atoms, different dance speed. But since we're doing a deep dive, I have to throw a wrench in the gears here, because nature loves exceptions.
I feel like you're leading up to helium. I saw that in the source material, and it blew my mind.
I am absolutely leading up to helium. Helium is the rebel of the periodic table. You'd think if you cool something down enough, reduce the jiggling, eventually everything should freeze solid, right? Stop the motion, lock the soldiers in place.
Theoretically, yeah. Absolute zero, the point where all heat is gone.
Well, helium refuses. You can cool helium down to absolute zero, and it will still remain a liquid. It will not freeze.
Wait, how is that possible? I thought absolute zero meant literally zero motion.
That's the classical idea. But this is where Feynman hints at quantum mechanics, which is his real playground. It turns out atoms cannot completely stop moving. The laws of physics, specifically the uncertainty principle, forbid total stillness.
Because if they stopped completely, we would know exactly where they are and exactly how fast they're going, which breaks the rules.
Exactly, you got it. And helium atoms are so incredibly light and their attraction to each other is so weak that this tiny fundamental quantum jiggle is stronger than the force trying to lock them into a solid crystal.
That is wild. So it's not just that they are fidgety, it's that the universe literally forbids them from standing still.
Exactly. Unless you apply massive, massive pressure to force them into a solid pressure, they will stay liquid forever, even at the coldest temperature physically possible. It's a glimpse into the weirdness that lives just underneath these simple rules.
Okay, so we've got solids, liquids, gases. But I want to bring this back to practical stuff. Every morning I blow on my hot coffee or my tea to cool it down. I never really questioned why that works. I just assumed my breath is cold, the coffee is hot, so it cools down. But what is actually happening at the atomic level?
This is one of my favorite examples from the lectures because it perfectly illustrates statistical mechanics.
Yeah.
Remember, in that cup of coffee, you have billions of molecules. Are they all moving at the exact same speed?
I would assume so. If the coffee is 150 degrees, they should all be doing 150 degree speeds.
No, and that's the trick. The temperature is just the average speed. But individually, it is pure chaos. Some are moving slowly, some are average, and some are absolute speed demons zipping around way faster than the rest of the crowd.
Okay, so we have some serious outliers.
Right. Now imagine one of those speed demons happens to be near the surface of the coffee and is moving upward. Because it has so much energy, it can actually punch through the surface tension. It breaks the attraction of its neighbors and flies off into the air.
And that's evaporation.
Yes. Now here's the math problem for you. If the fastest, most energetic guys leave the party, what happens to the average energy of the people left in the room?
The average drops, the vibe goes down.
Exactly. The average motion decreases. And what is motion?
Heat, so the liquid cools.
Bingo. When you blow on the coffee, you are physically sweeping away the steam. You're moving the guys who just escaped out of the way so that more fast ones can fly out without bumping into them and falling back in. You are systematically culling the herd of its most energetic members.
That is a ruthless way to look at breakfast. I'm just evicting the high-energy atoms so the rest can chill out.
It works perfectly. And Feynman contrasts this with a closed system. Imagine you take that coffee and you screw a tight lid on it. The fast ones still fly out, but now they hit the lid and bounce back in.
So they get trapped in the airspace above the liquid.
Right, and eventually you have just as many energetic atoms diving back into the coffee as you have flying out. The temperature stops dropping and the liquid level stays exactly the same.
And that's what we call equilibrium.
That is equilibrium. It looks like absolutely nothing is happening from the outside, but inside it's a busy airport. Departures equal arrivals perfectly.
I love that image. Okay, so we've moved atoms around, we've heated them up, cooled them down, evaporated them, but they are still the same atoms. Water is still H2O. What happens when the atoms decide to actually swap partners?
Now you're leaving pure physics and stepping into chemistry. Feynman defines a chemical reaction so simply. He just calls it the rearrangement of atomic partners.
Sounds like a square dance.
A very violent square dance. Let's look at fire. What is fire, really? We see the light, we feel the intense heat. But what is the atomic event that causes it?
Well, I know burning wood involves carbon and oxygen.
Right. Carbon, which is what wood or coal is mostly made of, and oxygen from the air are deeply attracted to each other. They desperately want to be partners. But usually they are too far apart or moving too slowly to hook up. But if you get them close enough and hot enough, snap.
They lock together.
They snap together with incredible force. Feynman really emphasizes this snap. It's not a gentle hug. It's like a massive magnet slamming into a refrigerator, but a billion times stronger relative to their size.
Right.
And when things snap together that hard, what happens to everything around them?
It shakes the whole neighborhood.
Massive vibration. Huge kinetic energy is released into the surrounding atoms. And as we just learned, massive jiggling equals what?
Heat. Intense heat.
That is fire. It's literally just the kinetic energy of billions of carbon and oxygen atoms violently snapping together to form a new partner, which is carbon dioxide.
It's amazing to think that a raging bonfire is just the sound of atomic clicking at a massive scale.
It really is, but here's the part that completely blows my mind. The exact same process rearranging partners creates totally different effects depending purely on the shape. Feynman brings up the smell of violets.
Yeah, that seemed like a hard pivot in the reading. We go from burning wood to smelling flowers.
But it's the exact same bricks. The scent of a violet isn't magic. It is a specific molecule, a very specific geometric arrangement of carbon, hydrogen, and oxygen. When that shape floats into your nose, it fits into a receptor like a key into a lock.
And my brain registers that specific lock, turning as flower.
Right, but if you rearrange those exact same atoms, just slightly change the architecture, maybe it smells like gasoline or rotten eggs or absolutely nothing at all. Chemistry isn't really about the substance, it's about the architecture, it's about where you put the bricks.
Okay, I'm going to play the skeptic for a second here. This is all beautiful imagery, the jiggling, the snapping, the keys and locks. But Feynman gave these lectures in the early 60s.
We couldn't exactly pull out a smartphone and take a photo of an atom back then. How do we know this isn't just a really convenient story? How did they know atoms were real before they could literally see them?
That is the million-dollar question. Feynman points to a few smoking guns, but the most famous one is something called Brownian motion. It dates all the way back to 1827. A botanist named Robert Brown was looking at pollen grains suspended in water under a microscope.
And the water was still.
Dead still. But the pollen grains were dancing. They were jerking around in random zigzag directions. For years, people thought maybe the pollen was alive.
Because what else would make it move on its own?
Exactly. But it wasn't alive. Decades later, Albert Einstein and others realized what was actually happening. Imagine you were looking at a giant beach ball bouncing around wildly in a stadium, but you were hovering in a blimp way too far away to see the crowd.
I just see the giant ball moving on its own randomly. Right. You would logically deduce that something invisible to you must be kicking it. The pollen grains were the beach ball, and the invisible kickers were the water molecules. The atoms were bashing into the pollen first from the left, then the right. We could see the effect of the atoms long before we could see the atoms themselves.
That is such a cool detective story. It's proof by inference.
Exactly. And that leads to Feynman's biggest overarching point. We've talked about water heat, fire smell, but Feynman argues that this atomic view unifies all of science. He uses an analogy that I think is the absolute most important part of the book, the chess game.
I remember this. He says the universe is like a grand chess game played by the gods, and we're just watching it.
Yes. Imagine you don't know the rules of chess at all. You just get to watch the board game after game. You see a bishop move diagonally. You see it happen 10 times. You write down law number 1, bishops move diagonally.
And that's basically a scientific theory.
It is. You feel good. You understand the universe. But then suddenly a pawn reaches the other side of the board and turns into a queen.
And you freak out because your rules are broken.
You completely panic. You say, my laws of nature are falling apart. But then you watch more closely and realize, there is a special underlying rule for when a pawn reaches the end. You revise your theory. Feynman says this is exactly what physics is. We are constantly finding new moves we didn't expect.
Like when we discovered quantum mechanics.
Exactly that. We thought the classical rules were permanent, things are solid and predictable. Then we watched the subatomic chessboard and realized, whoa, down here, things can be in 2 places at once. We had to rewrite the entire rule book.
Now, the source material actually brought up a critique of this by an educator named Richard Felder. He talked about how Feynman's approach highlights the frontier of ignorance.
Yes, Felder pointed out that Feynman wasn't just teaching facts, he was teaching scientific critical thinking. Physics is not Euclidean geometry where the rules are set in stone from day one. We have to be comfortable with approximations and constantly correcting our models.
So how does this chess game apply to, say, biology? Because a frog feels very different from a rock.
Well, for a long time, people thought life was magic. They thought there was a vital spark. But the atomic hypothesis killed that idea. Feynman is very firm on this. Everything that living things do can be understood in terms of the jiggling and wiggling of atoms.
That feels a little cold, like, are we really just bags of chemistry?
We are highly organized bags of chemistry. Think about it. How does a muscle contract? It is just a protein molecule changing shape, rearranging its atomic partners because of a chemical reaction. How do nerve signals travel to your brain? It's just ions, which are charged atoms flowing across a cellular membrane.
So biology is really just incredibly complex chemistry.
And chemistry is really just the complex behavior of atoms, which is physics. It is a hierarchy of complexity. The exact same laws that explain why the stars burn explain why your body stays warm. It's all the exact same game.
The stars thing is a great example, actually. We used to think stars were made of ether or some divine heavenly material.
Right until we developed spectroscopy. We pointed a prism at the starlight and saw the exact same spectral fingerprints of hydrogen, helium, carbon. The exact same stuff floating in your water glass is burning in the core of the sun. The universality of it is staggering.
What about the brain, though? Psychology. Does Feynman think that boils down to atoms, too?
That is the absolute frontier. Feynman admits that while the nervous system is completely physical and made of atoms, it's so complex that we just can't predict it yet. It's like trying to predict the outcome of a chess game where there are billions of pieces on the board. The fundamental rules are the same, but the game itself is too hard to calculate.
He also mentioned the 4 fundamental forces running all of this, right? Gravity, electromagnetism, the weak interaction, and the strong interaction.
Yes, those are the current core rules of the chess game as we understand them. They dictate how all these atoms pull and push on each other. But again, they are just our best approximations right now.
Which brings up a thought I had while going through all this. If we are just watching this cosmic chess game, and we keep finding new rules like castling or quantum mechanics, does the game ever actually end? Do we ever find the entire final rule book?
Feynman suggests that we might not, and that ties back to what Felder admired about him. We are constantly pushing into that frontier of ignorance. We are just peeling back layers of an infinite onion. We used to think atoms were solid, unbreakable balls. Then we found protons and electrons. Then we smashed those and found quarks. Now we're looking at string theory and quantum fields.
So every single time we ask, what is it made of, the answer just reveals a smaller, more complicated puzzle piece.
Precisely. And Feynman loved that. He didn't want all the answers to be done, filed away. He loved the mystery of it. He argued that to do science, you have to be completely comfortable with uncertainty. You have to be okay with saying, this is my absolute best guess for the rules right now, but I am perfectly willing to be wrong tomorrow.
That really seems to be the defining difference between dogma and science. Science is fully prepared to admit the rulebook was wrong.
It has to be. If the data shows the pawn turning into a queen, you cannot deny it. You have to change your understanding of how the world works to fit the board.
So bringing it all the way back to that cataclysm we started with. All things are made of atoms. It's not just a trivia fact about matter. It is a fundamental tool for thinking.
It really is. If you know that one sentence, you know that heat is motion. You know that chemical reactions are just rearrangements. You know that the stars and the trees are connected by the exact same laws. You could theoretically rebuild steam engines, chemistry, medicine, and electricity just from tracing the implications of that one single insight.
It honestly makes me look at the room around me differently. I'm looking at this wooden desk, and instead of solid wood, I'm trying to visualize billions of shivering soldiers locked in a grid.
And the air you're breathing right now is a relentless bombardment of nitrogen and oxygen molecules bouncing off your skin. And the sun shining outside is a nuclear furnace of hydrogen atoms violently smashing together. It is a very, very busy universe once you put the glasses on.
Ideally, we won't actually need to rebuild civilization from a single sentence anytime soon. But if we ever do hit that hard reset button, I think Feynman definitely picked the right one.
I'd have to agree with you. Though wash your hands is still a very close second in my book.
We can definitely add that as a footnote for the survivors. Everything is made of atoms, and please use soap. Thank you so much for taking this deep dive with us today. It has been an absolute mind-bender.
Always a pleasure to watch the grand chess game with you.
Keep observing the moves, everyone. We'll catch you on the next deep dive.